Welcome back to A Slice of Physics. With the basics of the simple harmonic motion concepts behind us, let's now take a look at the energy considerations of a simple harmonic motion. We're going to understand what energy transformations take place as a mass oscillates on a spring. We will see that potential and kinetic energy exchange with each other, and so we will also take a look at where are these two kinds of energies maximum and where are they zero. And then we will see how we can use this to derive a very useful expression between the period of oscillation, the spring constant, and the mass that's oscillating. All right, I'm going to use this image from the textbook to explain this concept. So here we are back at the horizontal spring with a mass tied to it, and the mass is pulled all the way to one end on the right. So x here would be plus a. Here it is 0 at the equilibrium position. And so I pull the mass all the way to plus a, let go. The mass is going to move to the left. As it moves to the left, it's going to speed up because the spring is pulling on it. So there's an acceleration. And then it passes through the equilibrium point with a maximum speed. So here my speed is maximum. And then it starts slowing down because the spring now pushes the mass back as it's moving to the left. And it comes to a rest at minus a over here. And so let me mark some of these points. So when it's here, v is 0. When it's here, v is 0. And those are called the turnaround points. And v is maximum when it is going through the equilibrium position. So let's talk about the energies that are involved here. So I've got two kinds of energies. I've got kinetic energy, which is the energy of motion, which is 1/2 mv squared. And then I got potential energy, which in this case will be the potential energy of the spring, which will be 1/2 kx squared, where x is the displacement from the equilibrium position. Kinetic energy is going to be 0 at the turnaround points, because at the turnaround points we see that the velocity is 0. So kinetic energy is 0 at turnaround points. And it's maximum at the equilibrium point because that's where it's moving the fastest. Potential energy, on the other hand, is going to be maximum at the turnaround points because it's a function of displacement, and displacement is maximum at those turnaround points. So it's going to be maximum at turnaround points. And it's going to be 0 at equilibrium, because at equilibrium, the displacement from equilibrium is 0, so x is 0, so the potential energy will be 0. So we can see that when kinetic energy is 0, potential energy is maximum. When kinetic energy is maximum, potential energy is 0. That makes sense because when this mass is oscillating, all it's doing is transferring one of these kinds of energies to the other. All right, and so the total energy, which is the sum of kinetic plus potential energy, can be written as 1/2 mv squared plus 1/2 kx squared. And that is a constant because there is no other form of energy, no external work being done. So energy is conserved. So the total energy is a constant. So you can see that at any point, if you take the kinetic energy, add it to the potential energy, you get the total energy. And with time or with position, the total energy does not change. So let's use this to get an important expression. We know that the kinetic energy maximum, K max, would be 1/2 mv max squared. And from a previous video, we saw that V max was simply 2 pi f times A. And so it'll be that whole thing squared. And the potential energy max would be 1/2 times k times a squared, because a is simply the max of the x. So given that when one is maximum, the other one is 0, so at this point, turnaround point at minus a, I've got potential energy at max, I've got kinetic energy at 0, and then at the equilibrium point, I've got potential energy at 0 and kinetic energy at the max. And so because these two things add up to the same number, we can see here that U max has to be equal to K max. So let me do that on the next slide. So we've got the expression that Umax plus 0. So remember, the total energy was constant. So I'm adding those two. So at the turnaround points, U is maximum, kinetic energy is 0. That has to be equal at the equilibrium point, 0 potential energy, but plus Kmax. So this gives me a useful expression that says Umax has to be equal to Kmax, which means 1/2 Ka squared has to be equal to 1/2 m Vmax squared, and Vmax was simply 2 pi Fa, the whole thing squared. So I can simplify this. I can cancel the 1/2s from both sides by dividing by 1/2. I can expand the squared term, so this becomes Ka squared equals m times, I'm just going to keep this as a square right now, so I'm just going to write this as 2 pi f squared times a squared. So I just simply expanded this to pull a out, and now I can cancel a from both sides. And I'm going to go ahead and solve for frequency. So in order to solve for frequency, I've got to write this as 2 pi f, the whole thing squared, will be equal to k over m. Some simple algebra here. I'm dividing both sides by m. So k over m is 2 pi f squared, so which means 2 pi f will simply be the square root of k over m, which means frequency would be 1 over 2 pi square root of k over m. So this is very useful. What it's telling me is that if I have a spring of known spring constant k, and if I have a mass m that is oscillating on that spring, it doesn't matter how far I pull it down or push it up. The a does not matter. Once I pull it up and leave it, as it oscillates, it's going to have a frequency of oscillation that is only dependent on the spring constant and the mass. And surprisingly, it is not dependent on how much I displace it from the equilibrium position. And the corresponding expression here, since I know that t is simply 1 over f, t, the period of oscillation, will be 2 pi times the square root of m over k. Now, why is this useful? We'll see some examples in class where we can use this to determine the mass of an object by tying it to a spring and seeing what the oscillation period is, and so on and so forth. There's a lot of uses for this expression. Or if I have a spring constant that I don't know what the k is, but I know the m, I can measure the t, and then I can calculate k. So the frequency or period of oscillation relates only to the mass that is oscillating and the spring constant of the spring it's tied to. It does not depend on amplitude. So in this video, we saw that potential energy, which is given by 1/2 kx squared, is 0 at the equilibrium position and its maximum at the turnaround positions. We saw that kinetic energy, which is 1/2 mv squared, is 0 at the turnaround points because velocity is 0 momentarily at those points. It's maximum at the equilibrium position. And then we saw that the total energy, which is the sum of those two, is a constant, which gave us this useful expression between t, k, and m, and t or f do not depend on a. Thank you.